there are a lot of fundamental constants in math and physics. Some of them are easy to describe, like pi, which is just the ratio of a circle's circumference to its diameter. And others are less easy to describe, like Euler's number, E. Now, there are countless YouTube videos out there about E, but very few of them give a nice intuitive understanding for what E really represents. I mean, I've never seen someone describe E in one simple sentence as you can with pi. So in this video, that's exactly what I'm going to attempt to do. Just as you can describe pi as the ratio of a circle's circumference to its diameter, by the end of this video, I'm going to describe E in one simple sentence that will give you a nice, deep, intuitive understanding for what it really represents. Let's start by looking at a few cases in physics and chemistry where we see E pop up. This will give us some hints as to what E is all about. Unlike pi, E isn't a ratio of any two numbers. That's why in a lot of math, physics, and chemistry, we never really see it multiplied by another number. Rather, we see it raised to the power of something else. Here's a few examples. E shows up in the equation for the voltage of a discharging capacitor. It also shows up in the Arrhenius equation, which describes how the rate constant of a chemical reaction changes with temperature. It also shows up in statistical mechanics with Boltzmann factors, which describe the probability of finding a particle in a certain microstate. So, for some reason, it makes a lot of sense to raise E to the power of other numbers. To find out why that is, let's look at the case study that pretty much everyone first learns about: compound interest. For just a moment, I want you to forget that we're even talking about Euler's number in this video. We'll see that during our discussion of compound interest, the concept of E as a fundamental constant will naturally arise. Let's suppose you put some amount of money, let's call it P for principal, into a high-yield savings account. In today's market, the highest interest rate you'll probably find for an account like this is around 5%. This means that if you leave your principal P in this account for 1 year, the bank will pay you an extra 5% of P back. In math terms, this means that the total money in your account after 1 year will be 1.05 times P. For example, if P was $100, after 1 year, your total account value will be $105. The bank paid you an extra $5 just for having your money in that account. After 2 years, your money will grow another 5%, meaning we multiplied the money you have in the account after year 1 by another factor of 1.05. This means that overall, relative to your principal P, your money grew by a factor of 1.05 squared, or 1.1025. Now, let's say instead of leaving your money in the account for 2 years, we only leave it in for 1 year, but the bank calculates interest a little bit differently. Instead of giving you an additional 5% of your principal at the end of the year, it pays you 2.5% of your principal every 6 months. In other words, your money multiplies itself by 1.025 twice a year. So, the total money you have in your account after 1 year is P times 1.025 times 1.025, which is equal to P times 1.050625. For the purposes of this problem, this is how we define compounding interest. Compounding interest means applying the interest more than once throughout the year, but splitting it up at equal intervals. We'll define the compounding frequency, n, to be the number of times in a year that the interest is applied. Every time it's applied, the rate it's applied at will be a fraction of the yearly interest rate, specifically the yearly rate divided by n. The reason I'm leaving our principal P as a variable here is that we don't really care about how much money you end up with after 1 year. We care about the factor your money grows by. In other words, we're concerned with this multiplicative factor, which for an interest rate of 5% compounded twice a year is 1.050625. Now, let's say instead, the bank compounds your interest every month, so your compounding frequency is 12. This means that it splits the annual interest rate of 5% evenly between 12 months, but then applies the interest 12 times in 1 year. 5% divided by 12 is about 0.42%. In 1 month, this corresponds to a multiplicative factor of 1 plus 0.42 over 100, which is 1.0042. We apply this interest to our total account value once a month, or 12 times a year. In other words, we multiply our total account value by 1.0042 12 separate times. This corresponds to a multiplicative factor of 1.0042 to the power of 12, or about 1.051161. Notice that for the past 2 examples of compounding, every time we increase the compounding frequency, the multiplicative factor also increases. We started at 1.05, then went up to 1.050625, and now we're up to 1.051161. So the question is, will it keep increasing forever? Well, let's find out. Let's say that the bank compounds your interest every day now. There's 365 days in a year, so we can follow the same process as before with n equals 365. And we find that our multiplicative factor ends up being 1.051267. Now, what if the bank compounds your interest every second? Well, with 60 seconds in a minute, 60 minutes in an hour, and 24 hours in a day, there's overall going to be 60 times 60 times 24 times 365 seconds in a year, or 31,536,000. If we apply this same math to get our multiplicative factor, we get 1.051271. So our multiplicative factor is still increasing, but it's increasing by less and less each time. It turns out that if we take this general formula for our multiplicative factor, where n is the compounding frequency, and keep increasing n indefinitely up to infinity, the multiplicative factor will converge to a single value, which is about 1.051271. I won't go into the proof for this because it requires calculus, so for now let's just accept it as a true statement. Now this is a really interesting result. It tells us that there's some sort of maximum multiplicative factor we can reach by compounding our interest infinitely many times. Okay, but what does that limit represent? Well, as we increase our compounding frequency, we're decreasing the amount of time before we apply the next round of interest. As long as n is finite, we're applying our interest at discrete time intervals, every year, every month, every day, every second even. But at the limit of n being infinity, we're now applying interest continuously instead of discretely. So it turns out that the maximum multiplicative factor for compound interest is also the multiplicative factor of continuously compounding interest. Okay, now we know what that limit represents. Let's step away from the example of compound interest for a second and generalize. What does compound interest represent? Well, interest rates are given as a percentage of the principal. This means that the amount by which something grows depends on its initial value. In other words, percentage increases can be described as self-referential growth, when a value increases by a proportion of itself, or in reference to its own value, hence self-referential. Compounding interest was therefore just an example of self-referential growth. This concept is equivalent to what most people simply call exponential growth. Exponential is a bit of a misnomer here because it implies that something is increasing really, really fast, which is true, but it doesn't address the fundamental idea behind the math, which is that a value is growing relative to itself. So exponential growth is really self-referential growth, and that's what I'm going to call it from here on out. Okay, so compounding interest is an example of self-referential growth. What are some other examples? How about bacteria? When bacteria reproduce, one bacterium splits into 2. Each bacterium only splits into 2 new bacteria at discrete time intervals, doubling the population of the bacteria at each interval. This is similar to the first case of compound interest I presented, where your money grows by 5% every year and you leave your money in the bank for more than a year. Our study of compound interest revealed that the multiplicative factor for continuous self-referential growth is the maximum limit of discrete self-referential growth. As we increased our compounding frequency n, we saw our multiplicative factor increase, but only up to a certain point, which we called the multiplicative factor for continuous compounding. Okay, this is great. Now let's go back to our compounding interest example. As we increased the compounding frequency, we got to a multiplicative factor of approximately 1.051271. This is our multiplicative factor for continuous self-referential growth at a rate of 5%, which we also know is a constant. Let's call this constant lambda. Of course, if I change this rate of 5% to some other number, say 10%, then the constant will change as well. So it's not really a constant, but we'll treat it as one for the next few minutes. Now, it becomes appropriate to question why we even care about this constant in the first place. In what real-world scenarios does a system grow continuously and self-referentially, like compound interest? Well, in a lot of scenarios, actually, particularly in physics and chemistry. But to be honest, that's not what really matters. What matters is that because the multiplicative factor for continuous self-referential growth is a constant, discrete self-referential growth at any rate can be described by an equivalent continuous self-referential process. Let's see how. We showed with our compound interest example that continuous self-referential growth at a rate of 5% has a multiplicative factor of 1.051271. Now, notice something here. If instead of putting our money in this continuously compounding account, we put our money into a discretely compounding account that instead pays out 5.1271% every year, that gives us the same multiplicative factor of 1.051271. That means that continuous self-referential growth at a rate of 5% is equivalent to discrete self-referential growth at a rate of 5.1271% as well, because they have the same multiplicative factor. In theory, we could also go the other way. Say the bank only gives us 5% per year on our money discretely once a year. We could ask a new question. In order to get the same multiplicative factor on our money every year for continuous compounding, what would their interest rate have to be? Well, we can figure that out pretty easily with our constant lambda. Lambda is the multiplicative factor for continuous self-referential growth at a rate of 5%. We need to find what power of lambda is equal to the multiplicative factor for discrete growth at 5%, which is 1.05. So let's set lambda to the power of some number x equal to 1.05. This means x would have to be log base lambda of 1.05, which is approximately 0.9758. Does that mean our equivalent rate of continuous self-growth is 97.58%? Well, of course not. That wouldn't make any sense. Continuous growth is always faster than discrete growth. So the rate of a continuous growth process would have to be less than the rate of an equivalent discrete process. So we know that lambda to the power of 0.9758 is equal to our multiplicative factor. But what does that tell us about the equivalent rate of continuous self-growth? Well, because lambda was the multiplicative factor for continuous growth at 5%, the power we took it to represents a fraction of that 5%. Why? Well, the concrete reason behind it requires some calculus again, which I intend to omit. Instead, consider lambda to the power of 1. That's the multiplicative factor for 1 times a rate of 5% continuous growth. Now consider lambda to the power of 2. That's equal to 1.10517, which you can work out on your own, is also the multiplicative factor for 10% continuous growth, 2 times 5%. That means, for the case I was describing, our equivalent continuous interest rate would be 0.9758 times 5%, or about 4.88%. So I'll say it one more time. This constant is incredibly useful for two reasons. One, it describes a multiplicative factor for continuous self-referential growth, which we know is a constant because it's a limit of discrete self-growth. And two, because discrete self-referential growth at any rate can be described as an equivalent continuous self-referential growth process. Altogether, this means that the multiplicative factor for any self-referential or exponential process can be described in terms of powers of our constant. Well, that's awesome, but obviously this lambda that we derived isn't E. Euler's number is approximately 2.718. Let's see how we can get to Euler's number. Let's look back at the example I was describing earlier. What is the equivalent rate of continuous self-growth for a discrete process that grows at 5%? To find that, I raised lambda to the power of some arbitrary number x and set that equal to 1.05. I found x, but then I had to multiply x by 5%, since lambda is a multiplicative factor for continuous self-growth at a rate of 5%. What if, instead, we set lambda to the multiplicative factor for continuous self-growth at a rate of 100%? Then, its exponent x would just be directly equal to the equivalent rate of continuous self-growth. So let's find what that number is. We're considering continuous self-growth at a rate of 100%. What's the multiplicative factor for this type of growth? It would be 1 plus 1 over n to the power of n as n approaches infinity. Let's calculate this number for different values of n. At n equals 1, it's just 2. This is equivalent to putting our money into an account that doubles it every year. At n equals 2, the factor becomes 2.25. At n equals 10, it becomes 2.594. At n equals 100, it becomes 2.705. At n equals 1,000, it becomes 2.717. And at n equals 1,000,000, it's approximately 2.718. Congratulations, we just derived E. So now, let's describe it compactly in one sentence. E is the multiplicative factor for continuous self-referential growth at a rate of 100%. We already showed why this constant is useful. But why did mathematicians pick the universal constant to be the factor for a rate of 100%? Why not pick lambda, which we derived earlier, which was the factor for a rate of 5%, to be this universal constant? Well, in principle, it doesn't really matter which you pick. To help explain why, consider the fundamental constant pi again. We could have just as easily chosen pi to be the ratio of a circle's circumference to its diameter times 0.05. The 0.05 is just a scaling factor and doesn't affect any fundamental equations. All that happens is that wherever we see pi, we'd swap it out with 20 times pi. The equation for a circle would then be 20 pi r squared, instead of pi r squared, for example. We just choose to define pi as the ratio of a circle's circumference to its diameter with a scaling factor of 1, because that's what makes our equations the most intuitive. In the same way, defining our constant, E, to be the multiplicative factor for continuous self-growth at a rate of 100%, 50%, 10%, or 5% doesn't fundamentally matter. The constant still represents the multiplicative factor for continuous self-growth, which is the important part. We choose to set it to a rate of 100% because that's the most intuitive. It ensures that any power of E is directly equal to the rate of continuous self-growth we are describing. E to the power of 0.05 is equal to the multiplicative factor for continuous self-growth at a rate of 5%, which is also the constant lambda we derived earlier. E to the power of 0.1 is the multiplicative factor for continuous self-growth at a rate of 10%. E squared is the multiplicative factor for continuous self-growth at a rate of 200%. And in general, e to the power of x is the multiplicative factor for continuous self-growth at a rate of x%. Now, what if x is negative? Then we'd be describing self-referential decay, when a value decreases relative to itself. These processes occur when you see e raised to the power of a negative number. Real-world examples of these include things like radioactive decay and the voltage of a discharging capacitor. We can also now see why log base e, or the natural log, is so important. Consider a number y, which we know is the multiplicative factor for some discrete self-referential growth or decay process. If it's a growth process, y is greater than 1. If it's a decay process, y is between 0 and 1. Then, the natural log of y would be the exponent of e that equals y, which means that the natural log of y is the rate of continuous self-referential growth or decay that describes a process equivalent to the discrete one. So, once again, let me summarize. The fundamental constant e is the multiplicative factor for continuous self-referential or exponential growth at a rate of 100%. As a fundamental constant, it's valuable for two reasons. Because a lot of natural processes grow or decay self-referentially and continuously, and because any exponential process growing or decaying at discrete intervals can be represented by a continuous process with an equal multiplicative factor. A lot of what I said here might take a while for you to fully digest, and you might even be more confused coming out of this video than you were coming in. I know I would be. This description of E is incredibly convoluted, but also incredibly deep. I suggest you try playing around with the formulas and numbers until all of this makes sense to you. The best way to get good at anything, including math, is just to practice after all. Speaking of practice, if you want even more exercises to strengthen your skills with any area of math or science, I highly recommend today's sponsor, Brilliant. Brilliant is an online platform where you learn by doing, with thousands of interactive lessons in math, data analysis, programming, and now even AI. Brilliant's uniquely designed platform combines first principles approaches with interactive lessons that make learning both effective and fun. One of my favorite courses on Brilliant is their course on calculus. It goes through each concept step by step, while providing interactive problems, giving you time to build intuition through practice. So sign up today at brilliant.org/foolishchemist and try everything Brilliant has to offer free for a full 30 days. You'll also get 20% off their annual premium subscription by using this link. Thanks for watching, and I'll see you in the next one.